Brittle deformation causes planar fixtures to show up in the rocks, fractures. And if there's no movement along that fracture, then we have a joint. Joints are often found in sets. So let's look down here at this image on the left. There are a bunch of cracks that run parallel to each other. So that is a joint set. So systematic joints occur in parallel sets. That's what that is. They're not always parallel. See the image on the right? It looks like there's been two phases of deformation in this image where you have one joint set running this way and then another joint set at this angle, one here, and then yet another joint set in this direction. The joint sets can be really evenly spaced joint sets like on the Colorado Plateau and these desert rocks, or like on the right, experience a series of deformations. There's lots of different orientations of the three different joint sets. In those joints, there can be percolating fluids. In those fluids, some groundwater is going to have ions in it, and those ions can precipitate out of solution and be deposited in those joints, and those are veins. Those are real common in the Appalachian Mountains, right? We see veins, quartz running throughout the rocks in this area. If there's movement along that planar fracture, then it's a fault. It's going to have displacement on it. When the displacement occurs, there's going to be an earthquake. So fault, if it happens all of a sudden, right? We did talk in our earthquake chapter about creep along faults, but for the most part, we're going to have a fault that has earthquakes. So this image here, it's showing earthquakes along the San Andreas fault system. Faults are going to happen in all the different stresses. So compression, tension, shearing are all going to have faults associated with them. The faults offset, they're different scales. So they can offset big pieces of the Earth's crust, or they can be found under a microscope just in deformation within different mineral grains. Either way, that offset is called displacement. So here's an example with the San Andreas, where displacement is hundreds of kilometers along the San Andreas Fault. Movement along the fault helps us classify the fault. We give it like a classification by the fault movement. So in this example, here is the fault. Here is a bed within the sandstone. It's offset this amount, and here it is on the other side of the fault. This side of the fault has moved down. This side of the fault has moved up. The sides of a fault, referring to in the last slide, are called the hanging wall and the footwall. In this image, they have a miner here in the middle. The miner's foot is in this tunnel, and their feet are in the footwall block, and their head is in the hanging wall block. You can draw a little person, like a stick figure, along a fault, and wherever their head is the hanging wall, and their feet are in the footwall. When we classify the kind of fault, it's either going to be a fault that has the hanging wall moving up or the hanging wall moving down. There can be different kinds of motion on the two sides, the hanging wall and the footwall, depending on the strain. And we classify the faults in three groups, really two main groups and then an extra one. Dip slip, where the movement on the fault is parallel to the dip of the fault. That just means the movement is along this dipping surface. The strike slip faults are faults that are going to be along strike, and that is just the horizontal plane within the hanging wall and the footwall. Oblique faults are going to be those that have both components, like a vertical and a horizontal movement associated with them. So the three kinds of dip-slip faults are reverse and normal faults are the main classification. A thrust fault is a special kind of a reverse fault. A normal fault, in the last little image here, has the hanging wall moving down with respect to the footwall. So let's go ahead and think ahead about the kind of strain there. Then if the hanging wall is moving down, then there's got to be extension. The crust is thinning in that case. Whereas in the two examples of these hanging wall moving up, a reverse fault, you're stacking up those beds on top of each other. The crust is thickening. There's been compression to move that hanging wall up. If the fault surface of the reverse fault is really low angle, that is a thrust fault. OBKB. So let's look closer at a normal fault. I'm going to turn my face off for now. Here is a normal fault. And the hanging wall has moved down with respect to the footwall. And the crust has thinned here. So that is a normal fault. Here is a reverse fault. We stacked these two sandstone layers would be continuous, but compression has moved them one on top of the other, so that is a reverse fault. These are examples of thrust faults. Okay, so a thrust fault is kind of a reverse fault, and the angle is really low, and one layer is being pushed up on top of another. We call those thrust sheets. So when you have continental collision, you can have orogenic episodes, or one orogeny after another in mountain building, and pile up those thrust sheets one on top of each other. This is exactly the kind of thing we have in Boone. We have thrust sheets to the east and thrust sheets to the west of us and north and to the south. And they have names like Pumpkin Patch. Strike slip faults are what we are going to find along transform fault boundaries, where you have that shear motion. And the strike slip faults like the San Andreas can cover like the whole side of the continent, but there's many, many, many tiny little strike slip faults that offset the mid-ocean ridges. They're classified in two different ways. They're either right lateral or left lateral. So if you're standing on one side of the fault and looking over the fault to the other fault block on the other side, you talk about the fault with respect to what the other side is doing. So in this case, here's someone standing on the far side of the fault, they're facing the other fault block and it's moving to the left, so that's a left lateral strike slip fault. And the opposite is true here, that's a right lateral strike slip fault. In the field, when we're out tromping around the woods and the mountains and trying to figure out the geology, there's certain things we can look for to recognize a fault. So this would be in this image, you know, those arrows are not going to be there, but we see this line cutting across these layers, and we can find where the layers are repeating, and we know that that is a little thrust fault there. There's also a bit of a fold here with some dragging along that fault surface. There it is. Another feature to look for to recognize a fault would be along the fault surface, there can be crushing up of the rocks right adjacent to the fault, and that would give us a fault breccia, like we see here on the left. If one fault block's stretches grooves into another fault block, we can get slickened sides. So these are slickened sides, and that would tell a geologist with those lineations which way the fault was moving. Another thing that's not as apparent in areas where there's lots of erosion, though, would be the fault scarp. So, and this is a desert environment here, maybe just an arid environment. And this surface here is the fault surface. So we could see that surface and know that there was a fault there. Maybe a little more investigation just to figure it out. And the same thing here. You would see this maybe in an area where there's not a lot of vegetation, where minerals have been flowing along that fault surface, and there's been some mineralization, kind of like a vein deposited along that surface. You would recognize those deposits. In the case of it sounds like we're mixing two things here, but there are faults that are going to occur in rocks that are sheared ductily. So here is a shear zone. That's ductile deformation happening in this. This is a shear zone within this rock, and the minerals have been sheared, and this line here represents movement along those slip along the two blocks there. Okay, so faults don't usually happen just in place, just one by itself. There's usually going to be a fault system, a group of faults. So this image here shows a group of thrust faults, and those thrust faults are boundaries for these thrust sheets, big packages of rock that have been stacked on top of each other during continental collision. So they're usually going to have a similar style of faulting. So there's 1, 2, 3, 4 thrust faults there. And then they may all kind of come together in one big detachment fault that kind of grounds the whole system. A fault system can also be with normal faults. This would be the case where we have extension. So there's a normal fault. And there are 1, 2, 3, 4, 5, 6 normal faults in here. 1, 2, 3, 4, 5, 6. The crust is thinning, so it's thick here, thin here, and those all also are going to be grounded in one big detachment fault. This kind of geology are called grabens, Horst and Grabens geology. And those happen in extension